Section 5.11 Softwar. World War III will be a guerrilla information war with no division between military and civilian participation. Marshall McLuhan. Section 5.11.1 To highlight how unique and different Bitcoin is, call it bit power instead of Bitcoin. To correct the information hiding problem and make it easier to understand the irreproducible properties of Bitcoin, the author suggests using a more technically accurate name for the proofs of power produced by proof-of-work protocols, bit power. The power part of bit power refers to quantities of physical power, aka watts, drawn out of the environment over time, modulated, and then digitally sampled by the network of computers running the physical cost function protocol, aka the hashing network. The bit part of bit power refers to the machine-readable bits of information generated from these sampled watts. Combining these two terms together, the word bit power literally means quantities of power, aka watts, converted into physically scarce, decentralized, and costly bits of information that can be transferred across cyberspace. This concept is illustrated in Figure 88, graphical illustration of bit power concept. Unlike most software specifications, it is important for the reader to understand that the term bit power is not a metaphor. The term bit power is meant to be taken literally, not metaphorically like most software abstractions, including the term Bitcoin. Creating a literal description of proof-of-work technology is helpful because the literal definition of bit power doesn't hide critical information about what's happening under the hood at the state mechanism level, like the Bitcoin metaphor does. Bit power refers to the real-world quantities of physical power drawn out of the environment and consumed by the network of computers running the bit power protocol, which is then converted into machine-readable bits of information that can be passed around cyberspace and called whatever people want to call it. Bit power isn't an imaginary concept designed to make it easier for people to understand one specific use case of the technology. It's literally power that people are using to program computers and store information to support any use case. The reason why the term bit power is not metaphorical is because the protocol leverages real-world quantities of physical power, as opposed to transistor states, to transmit, receive, and store bits of information. Like many features of the Bitcoin protocol, the term bit power is a little confusing because it's recursive. Power serves as both the underlying state-changing mechanism and the symbolic meaning assigned to that state change using machine code. When utilizing bit power protocols like Bitcoin, people are not just utilizing state-changing transistors to store bits of information and then arbitrarily choosing to describe those bits of information using a metaphor. Instead, they are utilizing real-world quantities of physical power, and then choosing to describe that real power as literal, albeit digitized, power. Bit power, therefore, doesn't technically qualify as hypostatization like coin does. As discussed in the previous chapter, hypostatization is when people treat an abstract idea as if it were a concretely real thing. When people describe bits of information using metaphors like coin, and then act like those coins are concretely real, they're hypostatizing. On the contrary, the term bit power describes bits of information as digitized power, which is something that is a concretely real thing. Large quantities of electric power drawn out of the surrounding electric power grid are real-world phenomena that everyone can independently see and measure directly. Bit power is therefore a digitized version of itself that can be utilized by machines inside the digital environment we call cyberspace. Again, it's confusing because it's recursive. Bit power is literal power, the digitized version of itself that can be wielded in, from, and through an abstract domain called cyberspace. This is a subtle but important distinction to call out, because it illustrates the previously mentioned concepts about how the coins created by so-called blockchain or cryptocurrency technologies are highly incomparable to Bitcoin's coins. To make it easy to see how dominant and nearly incomparable the Bitcoin protocol currently is in comparison to other cryptocurrencies, simply call it bit power instead of coin. Using this non-metaphorical naming convention, it is easier to see that bit for bit, no other bits can claim to represent remotely as much physical power as Bitcoin's bit power. As of this writing, Bitcoin represents 94% of the hash rate of all physical cost function protocols combined. Since hash rate doubles as a proxy measurement for the quantity of real-world power consumed by the network and converted into bits of information, this means the Bitcoin network is currently 16 times more powerful than all other proof-of-work protocols combined. The top contenders are currently Dogecoin, Litecoin, Bitcoin Cash, Monero, Ethereum Classic, Dash, and Zcash. This is noteworthy because public perception of Bitcoin's incontrovertible dominance in global adoption has been skewed by people who misunderstand, deliberately ignore, or attempt to marginalize or condemn Bitcoin's power usage. If one were to ignore or marginalize Bitcoin's power output or try to arbitrarily categorize it as merely a blockchain or cryptocurrency, then Bitcoin would appear to be one of thousands of cryptocurrencies with no discernible lead. However, if one were to account for the power output and actually recognize it as the primary value-delivered function of the protocol, then Bitcoin is clearly the dominant protocol. This concept is illustrated in Figure 89, illustration of the difference between public perception and reality of Bitcoin's dominance. Considering how Bitcoin's primary value-delivered function is to produce physically costly bits of information, trying to create a more energy-efficient version of Bitcoin would defeat the point of Bitcoin. For this reason, those who claim that Bitcoin needs to become more energy efficient are highlighting their own lack of understanding about what the purpose of this protocol is, and how it reverse optimizes bits to make them physically costly. This also implies that the repeated attempts to duplicate the Bitcoin protocol which fail to produce the same physical power output of Bitcoin, only serve to further show how dominant Bitcoin has become as the most widely adopted proof-of-work network. Michael Saylor, MIT 87, famously summed this up in 2021 when he declared there is no second best. Section 5.11.2. If power projection theory is valid, then bit power is extraordinarily valuable. It's worth repeating that of today, the concepts presented in this thesis are just theories. However, if these theories hold up to scrutiny within the computer science community, then this would imply that bit power protocols like Bitcoin fundamentally represent a new power projection tactic, a clever way to impose physical costs on other people through their computers by turning physical power itself into bits of information. When someone describes bit power, they are technically describing the real-world emergent properties and effects of physical power in a machine-readable format that can be controlled and projected against others in, from, and through the Internet. If these theories prove to be valid, then it means sapiens have figured out how to harness physical power to increase their cost of attack and lower their BCRA to keep themselves secure when operating in the virtual domain simply by choosing to treat real power as bits of information so that it can be wielded in an imaginary domain called cyberspace. It's a simple concept. To project real power in a virtual world comprised of nothing but bits of information, convert power itself into bits of information. Herein lies a core insight about physical cost function protocols like Bitcoin. Adoption of these protocols means entire populations of people are projecting real-world quantities of physical power against each other to impose real-world physical costs on each other, but doing it electrically rather than kinetically via the cyber domain. Agrarian society appears to be doing this transnationally, in a non-lethal way which doesn't look like any physical power projection capabilities of the past. This would imply that a global-scale physical power competition is being waged, and nations don't appear to be aware that it's happening because the battlefield is inside the disembodied virtual reality of cyberspace, where nobody can be physically harmed and things are easily hidden by abstractions and metaphors. If, for the sake of argument, we accept the author's theories as valid, then it begs the question, over what exactly is agrarian society competing? To answer this question, the author further examines physical cost function design concepts produced by Hal Finney and Satoshi Nakamoto. Section 5.11.3. The Gabriel's horn paradox shows it's logically possible to be infinitely scarce, yet infinitely scalable. An important feature to note about Nakamoto's design of Bitcoin is that the bit power it produces is supply capped, making it perfectly scarce. Paradoxically, that same supply capped quantity of bit power is also infinitely scalable. Despite having a strictly limited supply, Bitcoin's bit power can accommodate any number of users and convert any amount of real-world physical power into bits. This is a logically counterintuitive emergent property that is made possible by the fact that bit power is digital and therefore has no mass. To better understand how this works, the reader is invited to reflect upon a phenomenon known as Gabriel's horn. A popular character who appears in the holy texts of all three Abrahamic religions is an angel named Gabriel. In Catholic traditions, Gabriel is a saint and archangel who wields a horn to herald the Lord's return to earth. Many artistic depictions of Gabriel show him wielding a long and slender heralding horn, and that horn doubles as a symbol of human salvation. In the field of mathematics, Gabriel's horn is the namesake of a special geometric shape. If you plot the function y equals 1 divided by x on a two-dimensional graph, chop off the resulting curve from the point where x and y both equal 1, and then rotate the curves across either axis, you get the famous volume of revolution known as Gabriel's horn. The reason why this geometric shape is called Gabriel's horn is simply because it bears a striking resemblance to Gabriel the Archangel's heralding horn. This is shown in Figure 90, Gabriel's horn. Gabriel's horn, the geometric shape, is noteworthy because it has special mathematical properties. The volume of the space inside the horn is fixed, but the surface area of the horn is infinite. This is a mathematically sound shape that could theoretically exist in three-dimensional reality. If it did exist, the volume of the horn could easily be filled with a fixed quantity of paint, yet its surface could never be completely covered in paint, no matter how much paint someone had. This is a logical paradox known as the Gabriel's horn paradox, aka the painter's paradox. Practical limitations in manufacturing prevent Gabriel's horn from being built, but the point still stands that it is a mathematically sound shape that could theoretically exist in three-dimensional reality. It would therefore be perfectly, but paradoxically, logical to design something with a fixed volume of supply, but infinitely expandable, thus infinitely scalable, surface area. Understanding Gabriel's horn paradox is key to understanding a very important feature about Bitcoin. Because of the logical constraints encoded into Bitcoin's software, the bit power produced by the Bitcoin protocol has the same paradoxical behavior as Gabriel's horn. Bitcoin's supply of bit power has a fixed volume, yet it can scale to accommodate any number of users and any amount of real-world physical power, and do this all while remaining infinitely divisible. No matter how much real-world physical power is consumed by the computers attempting to solve Bitcoin's hash function, the total number of sequentially reusable bits of coin produced by the protocol to account for that power expenditure remains completely fixed. These dynamics create a logical paradox that is difficult for some to understand. The total quantity of real-world physical power, aka watts, consumed and accounted for by the protocol is theoretically infinite, but the total quantity of bit power exchangeable in cyberspace is fixed. At the same time, even though the total supply of bit power remains fixed, an unlimited number of people can have access to infinitely smaller pieces of it that can also account for infinitely larger amounts of power. A single bit of bit power produced by the Bitcoin protocol can scale to represent theoretically unlimited quantities of real-world physical power. And because bits have no mass and are infinitely divisible via logic, then 1. Everyone in the world can access Bitcoin's bit power, and 2. Everyone who accesses any amount of bit power has infinitely scalable physical power projection capacity. Instead of converting a practically unlimited supply of physical power, aka watts, into a virtually unlimited supply of bit power, Nakamoto's design intentionally utilizes the Gabriel's horn paradox. At first glance, Nakamoto's design appears to break the laws of physics. However, the Gabriel's horn paradox proves that the design is mathematically sound. One way to better intuit the paradoxical behavior of Nakamoto's design is to abstract the bit power it produces as surface area on Gabriel's horn rather than an ordinary geometrical shape like a coin. Nakamoto's physical cost function protocol takes an infinitely expandable quantity of physical power drawn from the environment and digitally converts it into a fixed volume of bit power that can account for an infinitely expandable supply of watts. So instead of visualizing Bitcoin's bit power tokens as coins, it might be more appropriate to visualize them as equally partitioned sections of surface area on Gabriel's horn, as illustrated in Figure 91, visualizing Nakamoto's bit power tokens as surface area on a Gabriel's horn. Now may be a good time to remind the reader that using object-oriented software design, computer programmers arbitrarily describe the complex emergent behavior of computer programs as if they were objects. They do this to make it easier to intuit the complex emergent behavior of their programs, because humans are used to living in a three-dimensional world with objects oriented around each other. This means the choice to describe bit power produced by the Bitcoin protocol as an ordinary object like a coin could just as accurately be described as equally partitioned segments of surface area on Gabriel's horn. Why do this? Because it highlights the protocol's paradoxically logical, complex emergent properties. The conversion of an infinitely expandable supply of physical power into a fixed supply of bit power creates two emergent properties that are important to explicitly call out. The first has already been discussed. Any infinitely minuscule amount of bit power can represent an infinitely large quantity of physical power. This is a useful behavior to have if the goal of the protocol is to maximize the physical cost associated with transferring, receiving, and storing each bit. A second emergent property worth calling out is that Bitcoin's bit power can't be diluted as more physical power is added to the system. Consequently, those who own or control Bitcoin's bit power automatically inherit the strength of all future physical power added to the system in a perfectly equal way. Expanding on these two important features further, since there's no limit to how far the surface area of Gabriel's horn can grow, there's consequently no limit to how far any tiny section of surface area can grow either. This means there's no limit to how much physical power any single amount of surface area can represent. Any infinitesimally small section of surface area on Gabriel's horn can expand or contract to represent any quantity of physical power drawn out of the environment by the computers running the protocol. Thus, there's no theoretical limit to how much physical power can be represented by a bit of bit power, no matter how minuscule the amount. The holder of a single bit of Bitcoin can theoretically project an unlimited number of real-world watts in, from, and through cyberspace. Moreover, even though the addition of more physical power into the system causes the percent magnitude of single units of physical power to decrease, this does not translate into cyberspace as a decrease in the percent magnitude of single units of bit power. The percent magnitude of any amount of bit power remains constant, because the total supply of bit power, as represented by the volume of the horn, remains fixed. Instead, the number of watts represented by each unit of bit power must increase to account for more physical power added to the system. The key takeaway from this design feature is that it creates a dynamic where it's not possible to dilute the physical power projection capacity of bit power, no matter how much additional physical power is added to the system. If you own 1 bit of bit power, you own the same percent magnitude of physical cost-imposing power in cyberspace, no matter how much the system scales or how much more physical power the system consumes. This creates a substantial first-mover advantage, as well as substantial path dependence that makes Bitcoin unforgiving to those who hesitate to acquire its bit power. This is another important feature which makes it more of a strategic imperative to position oneself as an early adopter. Combining these two emergent properties together creates a logically sound but paradoxical dynamic that could make Nakamoto's version of bit power disproportionately valuable as a cybersecurity asset. Recall from section 5.6 that proof of power, aka bit power, represents proof of physical cost of attack. If the supply volume of bit power is fixed, then owning bit power means automatically inheriting any of the physical cost-imposing power added to the system in the future, with no theoretical limit to how much physical cost any amount of bit power can impose on other people, computers, and computer programs. In other words, owning Nakamoto's supply-capped bit power means being able to leverage infinite amounts of real-world physical power to impose real-world physical costs on others in, from, and through cyberspace, without the capacity for it to be diluted by adversaries in the future, no matter how much it scales. Figure 92, logically paradoxical power conversion dynamics of Nakamoto's Bitcoin protocol, provides an illustration of the paradoxical dynamics of how Nakamoto's design converts physical power to bit power. The real-world, infinitely expanding quantity of physical power, aka watts, consumed by Bitcoin's hashing network can be visualized as an infinitely expanding volume taking the shape of a cube. Nakamoto's protocol takes this infinitely expanding volume of power, visualized here as blue cubes, and digitally converts it into a fixed supply volume horn with infinitely expandable surface area. In other words, Gabriel's horn. The left side of this image illustrates the expanding supply volume of physical power drawn out of the environment by computers running Nakamoto's protocol. This is represented as a cube with volume expanding towards infinity. If we were to isolate one unit of that cube's volume and measure its percent magnitude as the total volume of the cube expanded towards infinity, then we would see the percent magnitude of that single unit of volume gradually fall to 0. In this image, we can see that the percent magnitude of 1 watt of physical power drops from 5% to 0% as the overall volume of electric power drawn out of the environment expands from 20 watts to infinity watts. Nakamoto's design digitally converts this volume of physical power into information, bit power, that is logically constrained as if it were the surface area of a Gabriel's horn. Here we can see how the digital representation of bit power in virtual reality can be implemented as infinitely expandable surface area on a fixed volume Gabriel's horn geometry, in contrast to the geometry of an infinitely expanding cube with infinitely expanding volume. This sleight of hand is possible because bit power is digital, in other words, disembodied or massless. If we were to isolate one segment of that horn's surface area and measure its percent magnitude over time as the total surface area of that horn stretched toward infinity, then we would see the percent magnitude of that single segment of horn surface area remain fixed. In this illustration, we can see that the percent magnitude of one segment of horn surface area remains fixed, even as it expands toward infinity. The bottom line is that Nakamoto's design creates a paradoxical but mathematically valid behavior that causes the protocol's bits to have unique and counterintuitive properties that are perhaps easier to intuit if visualized as sections of surface area on Gabriel's horn, rather than ordinary objects like coins. By visualizing a bit power as if it were a segment of surface area on Gabriel's horn, it perhaps becomes easier to understand the paradoxical behavior caused by digitally converting infinitely scalable quantities of real-world physical power into a fixed supply of bit power. The most important takeaway of this design concept is that an infinitesimal amount of bit power can represent an infinitely large quantity of physical power for any number of users without dilution, giving it potentially disproportionate strategic value as a cybersecurity asset that is both infinitely scarce and infinitely scalable. This creates an unforgiving first-mover advantage and path dependence that is important for people to understand. Section 5.11.4 Bit power could function as a digital age freedom-fighting technology. We can win a major battle in the arms race and gain a new territory of freedom for several years. Satoshi Nakamoto. Summarizing the core theoretical concepts about Bitcoin presented so far, bit power protocols like Bitcoin look inefficient to those who might not understand the complexities of computer theory, cybersecurity, agrarian power dynamics, human metacognition, or the basics of how living organisms establish dominance hierarchies to manage control over their resources. Consequently, people don't understand how and why people would be inclined to summon large quantities of electric power from the environment, convert it into machine-readable bits of information, and use it for systemic security purposes, particularly to countervail the threat of people wielding too much abstract power via the computers they program. As theorized in previous sections, the electric power deficits produced by proof-of-work protocols appear to turn the global electric power grid into a planetary-scale state-changing mechanism that can transmit, store, and receive machine-readable information, thus adding a physically constrained and thermodynamically restricted state space to cyberspace, with complex emergent properties that are physically impossible for ordinary computers to replicate. A physically constrained and thermodynamically restricted state space within cyberspace is a novel capability that appears to have been missing from cyberspace thus far, and society appears to be starting to grasp the broader social, technical, and strategic security implications of this capability. This thesis is proof. The bottom line up front is that, for the first time, people appear to have discovered how to project physical power in, from, and through cyberspace by converting global power itself into bits. Thanks to protocols like Bitcoin, people can utilize bits of information that have been reverse optimized to be physically expensive to produce, to impose severe physical costs on belligerent actors who keep trying to interfere with people's bits or systemically exploit people through software. These physically expensive bits could also be used to prove the presence of real-world properties, such as scarcity and decentralization, in an otherwise artificial domain where ordinary computers can only be programmed to present the illusion of scarcity and decentralization. One clear application for this capability is security against cybercrime and cyber tyranny. Bit power protocols make it possible to project physical power in a unique way to keep oneself secure against computers, computer programs, and computer programmers by physically constraining them. Rather than having to rely on permission-based abstract power hierarchies, which can only logically constrain certain unsafe or exploitable control actions, by giving only a few people with high rank and special administrative privileges the permission needed to execute them, software engineers now have a way to design control structures which can apply physical constraints and use physical power, not abstract power like rank or admin rights, as the basis for establishing control over software. Just like animals in nature and people in agrarian society leverage the systemic benefits of physical power to settle disputes, manage resources, and establish dominance hierarchies in shared objective reality, bit power protocols like Bitcoin theoretically make it possible for people to utilize this exact same strategy in cyberspace. We can now settle disputes, establish control authority, and determine the legitimate state of ownership and chain of custody of bits the old-fashioned way, through real-world physical power competitions. And remarkably, we can do it without causing injury, because the protocol utilizes electric, in other words, non-destructive, power rather than kinetic, in other words, destructive, power. Using bit power protocols like Bitcoin, which convert real power into digitized power to wield in a digital domain, it is theoretically possible to design physical power-based resource control structures that physically constrain unsafe or insecure control actions and physically constrain people with abstract power. No longer do people have to design systemically exploitable abstract power hierarchies created by computer programmers that give special permissions to specific people and trust them not to abuse it. This is important because logically constrained software control structures and software-defined abstract power hierarchies are demonstrably prone to systemic exploitation, either externally, via hackers, or internally, via abusive system admins or insider threats. Accelerating cybercrime incidents have demonstrated how challenging software security is when people don't have the ability to impose physical constraints. We have discussed how it's impossible to logically constrain something against the exploitation of logic, whereas it's easy to physically constrain something against the exploitation of logic. Simply make it impossible to justify the physical cost of exploiting logic. We may be starting to see these same principles hold true for the emergence of cyber tyranny. There's no clear way to escape from massive-scale systemic exploitation of our software exclusively by writing more lines of code. The root cause of cyber tyranny would be the same as the root cause of our challenges with cybercrime. Users have no way to physically constrain or thermodynamically restrict the abstract power of software administrators who are abusing the trust we must necessarily put into these people not to exploit us through our bits. If we are to mitigate the threats of cybercrime or cyber tyranny, it's necessary for us to adopt some type of protocol which will empower people to secure their bits physically by projecting physical power in, from, and through cyberspace to impose severe physical costs on those who exploit our computing systems. And that's precisely what the Bitcoin protocol is doing. Physically countervailing oppressive abstract power hierarchies is the American way. The United States gained its independence by imposing severe, physically prohibitive costs on high-ranking people who were exploiting them through their abstract power hierarchy. Thanks to Bitcoin, Americans now appear to have gained the same capability of digital freedom fighting for cyberspace. Of course, The threat of tyranny and the need for revolution was not just exclusive to Americans. Agrarian society has suffered through several millennia of systemic exploitation, from people creating, wielding, and abusing their abstract power. Revolutions make it clear that societies must remain capable of and willing to project physical power against their ruling class if they want to keep themselves secure against systemic exploitation, abuse, and oppression from their ruling class. A major difference between revolutions of the past and revolutions in the digital age is the technology used to exploit people and to physically resist that exploitation. The digital age ruling class is the technocratic group of people who control our computers through the software they write. It's the people who administer our software, including but not limited to governments. In previous chapters, we explored how self-domestication is a real threat. Society's lack of ability or inclination to project physical power in any domain to reduce their BCRA is a well-known systemic security hazard that can be independently and empirically validated. The exact same systemic security hazard exists for cyberspace. Without the capacity or inclination to project physical power and impose physical costs in, from, and through cyberspace, a technocratic ruling class of neo-god kings have an opportunity to domesticate and systemically exploit human populations at a massive and unprecedented scale, simply by having physically unconstrained control authority over their computer networks. Fortunately, thanks to electro-cyber power projection protocols like Bitcoin, people now appear to have the technology they need to countervail this threat. People could use this technology to countervail abstract power hierarchies when they inevitably become too exploitative. This technology could become instrumental to the design of different control structures or computer networks, which make it impossible to justify the physical cost of exploiting people through their software. If these theories are valid, then the only thing preventing our digital age global society from starting to physically secure themselves against the emerging threat of cyber tyranny is for them to 1. Recognize the threat, 2. Recognize they have this capability, and 3. Start using it. From the perspective of power projection theory, it seems inevitable that we are going to have a digital age revolution, a soft war for zero trust, permissionless, egalitarian, and decentralized control over our worldwide web of computers. As Nakamoto himself declared, Bitcoin is part of an arms race which could help people gain new territory for freedom for years to come. The author hypothesizes that agrarian society is now beginning to recognize that they have the capacity to project power in, from, and through cyberspace to secure themselves against the threat of systemic exploitation of their computer networks. The technology appears to be hiding in plain sight by masquerading as a peer-to-peer electronic cash system. To that end, the purpose of this thesis is to illustrate how physical cost function protocols like Bitcoin represent far more than just monetary technology. They represent physical power projection technology. And if history is any indicator of what's to come, the emergence of a new form of physical power projection has the potential to be far more unique, valuable, disruptive, and strategically essential than a new form of money, especially as the global population continues to spend exponentially more time using computers. The socio-technical and national strategic impacts of Bitcoin envisioned by the author have little to do with finance. This is not a grounded theory about money, it's a grounded theory about power. The author asserts that the Bitcoin protocol is first and foremost a physical power projection protocol, and bit power represents the ability to physically countervail abstract power and resource control authority of software administrators, and physically decentralize the cyber empires they're trying to lock people into via cyberspace. This not only impacts businesses, but it also impacts governments. Because of proof-of-work technology, entire populations are now literally empowered to impose real-world physical costs on other people and programs via cyberspace, to include computer programs controlled by governments. Agrarian society can now strategically secure itself against innumerable attack vectors encoded, often intentionally, by any type of computer programmer, regardless of who they work for. Therefore, the author asserts that Bitcoin is not monetary technology. At least, money doesn't appear to be its primary value-delivered function. Instead, Bitcoin appears to be an electro-cyber freedom-fighting technology. In other words, Bitcoin isn't a monetary protocol. It's a bit power protocol. It creates a new base layer foundation to the Internet by adding a new state mechanism to the bottom of the Internet tech stack, which physically constrains the World Wide Web of computers. It just happens to be the case that the first operational and widely adopted use case for this novel Internet infrastructure is to restore peer-to-peer financial payments. But it's reasonable to expect many more use cases to follow. In what could have been an intentional sleight of hand, and perhaps one day be reflected upon as the most impressive Trojan horse since the Trojan War, the decision to frame Bitcoin as only a peer-to-peer electronic payment system has motivated transnational human society to subsidize the development of a global-scale electro-digital defense industrial complex that literally empowers people with zero-trust, egalitarian, and permissionless access to bit power. Extraordinary quantities of physical power are now being drawn from a planetary-scale state mechanism and converted into physically costly bits of information that anybody can utilize to impose severe physical costs on people and programs in, from, and through cyberspace. With this new Internet architecture, people are capable of physically securing themselves against hackers, as well as physically securing themselves against systemic exploitation from an emerging technocratic ruling class. And they can do it all without spilling a single drop of blood. Power projection theory is a bold theory, but it's a grounded theory. It blends military theory, political theory, and computer theory together using first principles and systems thinking. If power projection theory proves to be valid, then Bitcoin represents the emergence of a new internet tech stack, which disrupts our perception of cyberspace from the bottom up. It's also a non-lethal form of freedom fighting that could empower people to physically resist tyranny and oppression in, from, and through cyberspace. By simply calling it a coin, this freedom-fighting technology has blossomed and grown under the noses of those who have made the classical mistake of expecting the next revolution to look like the last revolution. Section 5.11.5 A vital new resource worth fighting for. Physical power can and has been used to establish zero trust and egalitarian control structures, which can't be systemically exploited like abstract power hierarchies can. The systemic exploitation of abstract power hierarchies has been a problem that has plagued society for thousands of years, and software-defined abstract power hierarchies are just as vulnerable to exploitation as abstract power hierarchies like governments are. Bit power protocols have a chance at counteracting the hazards of abstract power hierarchies, just like physical power has already done for thousands of years. If someone were to design an open-source protocol where everyone has zero trust, egalitarian, and permissionless access to bit power, it could be extraordinarily valuable as a cybersecurity asset. With these concepts fresh in our minds, the author will now revisit the design of the physical cost function protocols designed by Back, Finney, and Nakamoto. As outlined in the previous two sections, attaching bit power, aka proof of work or proof of power receipts, to sensitive control actions issued by a computer program makes it possible for engineers to design new types of control structures which can physically constrain the execution of virtually any control signal in cyberspace, making them too physically costly to systemically exploit and thus more systemically secure. This is a compelling security capability that appears to have been missing in computer science until the emergence of physical cost function protocols, aka proof of work or bit power protocols, like the one built by Back. The first iteration of Back's bit power protocol issued non-sequentially reusable bit power that were stamped onto individual control actions for one-time use. This design requires computers to consume electricity and solve the hash cost function for every individual control signal that the protocol was used to physically constrain. This presents a technical problem. It makes any computer program utilizing the protocol run too slowly to be practically useful. If people had to wait several minutes for a computer to solve a difficult hash function algorithm every time they wanted to issue a command, then the protocol would likely not be adopted because of how impractical it would be to use. Recognizing this technical issue with Back's bit power protocol design, a computer engineer named Hal Finney created a more practical version of a bit power protocol where the proof of power receipts, aka proofs of work, are sequentially reusable. That way, instead of having to wait for a computer to solve the hashing cost function each and every time someone wanted to send a command, they could simply present a proof of power token to show that the hash cost function was solved at some time in the past. Finney understood that a sequentially reusable version of bit power would have the same effect of imposing severe physical costs on the computer trying to execute a command, but it would remove the lag of having to resolve the hash cost function at the point of issuing a command. It's worth noting that this was not a new idea. This is precisely what Jules and Jacobson described as a bread pudding protocol in their 1999 paper, which introduced the term proof of work. The main difference is that Finney actually built it, whereas others merely theorized. Using the same naming convention created by Jules and Jacobson and adopted by Back, Finney called his design concept reusable proofs of work, RPOW. The bottom line is that a major advantage gained from Finney's sequentially reusable bit power protocol was speed. In Back's design, bit power is destroyed after the execution of a single command. At scale, this creates an impractically slow system where the hashing algorithm must be solved to execute every new command. When bit power is sequentially reusable, it becomes possible to make a much faster and more practically useful system while still preserving the primary value-delivered function of physically constraining computers by imposing severe physical costs on the execution of specific commands. Another major advantage gained from Finney's reusable proof-of-work design concept was that his version of bit power could be used as a general-purpose proof-of-power protocol that could serve multiple different use cases, rather than exclusively one application at a time, such as reducing email spam. Finney describes this advantage as follows, quote, "Normally, proof-of-work tokens can't be reused because that would allow them to be double-spent," Finney writes. But reusable proof-of-work allows for a limited form of reuse, sequential reuse. This lets a proof-of-work token be used once, then exchanged for a new one, which can again be used once, then once more exchanged, etc. This approach makes proof-of-work tokens more practical for many purposes, and allows the effective cost of a proof-of-work token to be raised while still allowing systems to use them effectively." End quote. Theoretically speaking, a single bit of sequentially reusable bit power can be utilized an infinite number of times for any number of different use cases. It could also be sequentially reused at such a high frequency that it could be visualized as a continuous stream of irradiating bit power, rather than individually discrete transfers of bit power. Reusable bit power protocols therefore have very attractive qualities that could serve multiple applications. Unfortunately, as is the case with most engineering decisions, the benefits gained from making bit power sequentially reusable also introduces a tough design challenge. By making bit power tokens reusable, Finney had to figure out a way to enable sequential reuse, while simultaneously prohibiting parallel reuse. Parallel reuse is a problem because if bit power can be reused in parallel, it would effectively defeat the purpose of the protocol. Each bit power would no longer be able to impose severe physical costs on computers, because they could be duplicated ad infinitum, diluting the physical cost associated with each bit power token down to zero. As a side note, this is the same reason why there has to be a hard cap on the supply of bit power. In other words, bit coins. Sequential reuse of bit power doesn't undermine the laws of thermodynamics, but parallel reuse does. Power can be transferred, stored, and reused in series, but it cannot be created or destroyed. Therefore, it can't be cloned or exist in two places at once. Considering how bit power's value is derived from its physical constraints, then allowing parallel reuse of bit power would logically undermine its value. The utility of proof of power is derived from the fact that the physical power expended to produce bit power is physically expensive, in watts, and thermodynamically restricted. This reverse optimization is what makes bit power unique, and gives it its irreproducible emergent properties. A custodian who can reuse bit power in parallel is someone who effectively has the ability to reproduce or clone real-world physical power out of thin air, and then use it in two places at once. These custodians would be breaking the real-world physical constraints of physics that are ostensibly imposed by the protocol, making them false or fraudulent representations of real-world physical power in cyberspace. Hence, one of the many reasons why people claim that alternative systems like proof of stake are fraudulent. Remember, the point of these protocols is to reverse optimize bits, to make them physically expensive to transmit, receive, and store. If these bits can be used in parallel, or there are not hard limits on their supply, or they are not extraordinarily energy-intensive to produce, then that defeats the point of the protocol. To mitigate the problems of parallel bit power reuse, Finney had to figure out how to design a protocol which enables sequential reuse of bit power while simultaneously constraining parallel reuse. From a systemic design perspective, this is exactly the same challenge that financial systems have. Financial systems must figure out a way to enable the sequential reuse of monetary notes while prohibiting parallel reuse, a form of fraud where users make counterfeit bills or deliberately write checks they can't cash. The financial community calls this the double spend problem. If we were to, arbitrarily, abstract bit power as coins, then we could say that Finney's primary design challenge was the same challenge faced by financial systems, finding a way to solve the so-called double spend problem. In order for Finney's reusable proof of power protocol to function properly, it would require the addition of a third step to the physical cost function protocol that Back's version didn't have, keeping track of the position of each bit power coin over time, to make sure they're only reused in series, not in parallel. In other words, Finney's physical cost function protocol had to instantiate a ledger which keeps track of the legitimate state and chain of custody of each bit power coin, to make sure they weren't being used in two places at the same time. This is illustrated in Figure 93. Illustration of the third step added by Finney's physical cost function protocol. Finney solved the double spend problem the same way financial systems solve the double spend problem, by having a trusted party keep account of the position of each bit power token to ensure they're not being used in two places at the same time. Unfortunately, this design choice introduces a significant systemic security vulnerability. It requires trust in a group of people with special permissions not to abuse their special permissions to exploit the system. In other words, Finney's design implemented yet another form of abstract power hierarchy, where people with imaginary power, in the form of special administrative permissions to add transactions to the ledger, have tacit control authority over bit power and its state of ownership and chain of custody. Like all abstract power hierarchies, this is a trust-based and inegalitarian resource control design, which creates a ruling class of administrators and a ruled class of users. The ruled class must trust their ruling class not to abuse their special permissions, because users are otherwise physically powerless to countervail them. Having just read hundreds of pages explaining how abstract power hierarchies are systemically insecure no matter how they're encoded, hopefully the reader can now appreciate why Finney's bit power protocol design was flawed from a systemic security perspective. Finney's reusable bit power protocol design was flawed for the exact same reason that governments or any other form of abstract power hierarchy is systemically flawed. They're trust-based, permission-based systems, which give people abstract power and control authority over a vital resource, and trusts them not to exploit it for their own personal advantage, despite an ever-increasing benefit for doing so. We have over 5,000 years of written testimony which says that abstract power hierarchies break down and become dysfunctional no matter how well they're designed, and no matter what logical constraints they try to impose through their rule sets. Bit power has the potential to be an extraordinarily valuable resource. By creating a ledger which keeps track of the legitimate state of ownership and chain of custody of each bit power token to allow for sequential reuse and prevent parallel reuse, then by restricting access to writing the ledger to a trusted third party, Finney created an abstract power hierarchy, where some entity has abstract power and control authority over the entire system, by virtue of their having control authority over the ledger, accounting for the position of each bit power token. His protocol created yet another abstract empire, where users must trust in a technocratic elite class of computer programmers, not to exploit their control authority over a potentially vital resource. Finney's design introduced useful features to bit power protocols like sequential reusability and the ability to pseudonymously register ownership of bit power using private key encryption. But at the same time, the system relied on a trusted third-party server to keep account of the position of each bit power token. Therefore, even though Finney's design successfully solved the double spend problem and introduced other useful features, the way the system solved the double spend problem had a glaring systemic security vulnerability, a vulnerability that a pseudonymous software engineer named Satoshi Nakamoto was quick to point out and resolve. Section 5.11.6 Let those with real power compete for control over ledger writing administrative privileges in a zero-trust, permissionless, and egalitarian way that will decentralize that control. Inspired by Back and Finney's design concepts, Nakamoto's design created sequentially reusable bit power and also accounted for the sequential state of ownership and chain of custody of bit power using a ledger, just like Finney's design did. However, the primary difference was that Nakamoto's design didn't logically constrain ledger writing administrative privileges to a trusted server wielding imaginary power. Instead, Nakamoto chose to assign these special administrative privileges to those who demonstrate they have real power, aka Watts. In other words, he instantiated a might is right, or favor the power projectors, pecking order heuristic for Bitcoin's control hierarchy, thus replicating the design of nature. Instead of creating an abstract power-based dominance hierarchy to manage the ledger, Nakamoto created a system where people with real-world physical power, aka Watts, engage in a global-scale physical power competition for ledger writing control authority in a zero-trust, permissionless, and egalitarian way. As a complex emergent benefit of this global-scale physical power competition, the special privilege of writing the ledger remains decentralized and impeachable, thereby empowering users with the ability to remain physically secure against systemic exploitation and abuse of those ledger writing privileges. Because physical power is unbounded, there is theoretically no limit to how many watts people can project to countervail the power of any other person or organization who might attempt to exploit or abuse these special ledger writing administrative privileges. Herein lies the cleverness of Bitcoin's design. The Bitcoin protocol empowers society to leverage physical power to battle for control authority over a vital new agrarian resource, bit power. Through this global-scale power competition, agrarian society decentralizes control authority over the ledger and achieves consensus on the legitimate state of ownership and chain of custody of bit power in a zero-trust, egalitarian, and permissionless way. By simply giving permission to write the ledger to those who win the physical power competition, Nakamoto solved the double spend problem in a way that doesn't make people as vulnerable to systemic exploitation and abuse of software administrators. With this simple design concept, the BCRA, benefit to cost ratio of attack, of the Bitcoin ledger writing privileges drops down to the point where it's impossible for attackers to justify the physical cost of attempting to exploit these privileges. The complex emergent benefit of this global-scale physical power competition for ledger writing administrative privileges is decentralization of control over bit power. In what could be described as an impressive display of design thinking, Nakamoto replicated the complex emergent benefits of warfighting by creating an electro-cyber version of it. He created a system where globally divided populations with completely different priorities and belief systems can engage in a physical power competition to establish physically constrained, balanced, and decentralized control authority over this potentially vital resource, to achieve global consensus on its legitimate state of ownership and chain of custody in a purely zero-trust, permissionless, and egalitarian way. To that end, what makes Bitcoin's design remarkable is not merely that it solved the so-called double spend problem or Byzantine generals problem. Section 5.11.7. The way Nakamoto solved the Byzantine generals problem could solve much bigger problems. Nakamoto is given credit for solving the double spend problem, without having to rely on a trusted third party to account for the chain of custody of sequentially reusable bit power. To accomplish this, he designed a system which utilizes a distributed network of nodes to manage the ledger, rather than relying on a trusted third party, a glaring security vulnerability with Finney's design. Of course, Nakamoto's decision to utilize a distributed network to manage the ledger introduced another design challenge. How do you get a distributed network of computers that can't be trusted to agree on the legitimate state of the ledger? In computer science, this challenge is what's known as the Byzantine generals problem. Because Nakamoto's protocol provided a viable solution to this challenge, Nakamoto is given credit for solving the Byzantine generals problem. However, the author asserts that crediting Nakamoto's Bitcoin protocol for solving the Byzantine generals problem undersells how significant it is. Using the core concepts of power projection theory, we can better appreciate why Nakamoto's design could be far more significant than merely solving a distributed computing challenge. This technology also has the potential to solve a much bigger challenge faced by society as a whole: a global, strategic nuclear kinetic stalemate. The design challenge which Nakamoto faced was the age-old challenge of establishing zero-trust, egalitarian, and permissionless access to a resource. Whoever has administrative authority over a bit power ledger implicitly gets control authority over people who depend on bit power. That control authority can be exploited. The ability to add transactions to the ledger doubles as the ability to deliberately withhold transactions from the ledger. This means the ability to add transactions to the ledger doubles as the ability to denial of service, DOS, attack users. By simply choosing not to add valid transactions requested by a given user, that user can be DOS attacked. Just by gaining permission to write the ledger, an entity gains a form of abstract power over people, in the form of special permission, which they can exploit to deny someone access to their property. Determining who gets to write the ledger therefore represents an extremely sensitive control action, with major systemic security implications, which must be properly constrained by a control structure design. From a broader systemic perspective, we can see that the problem Nakamoto faced with determining how to establish ledger writing control authority over the bit power ledger was not merely a problem faced by computer scientists working with distributed computing networks. This is a problem that has been plaguing human society for thousands of years. This is a problem that life itself has wrestled with for the past 4 billion years. People miss this critical insight because they frame Nakamoto's design challenge as this: how do you get a distributed network of computers to agree on the legitimate state of the ledger. But an equally accurate way to frame Nakamoto's design challenge has a far bigger scope. How do you establish control authority over a resource in a zero-trust, egalitarian, and permissionless way that doesn't utilize a systemically exploitable abstract power hierarchy? Establishing zero-trust, egalitarian, and permissionless control authority over a resource is fundamentally a question about how to settle disputes without the use of abstract power like rank. This is fundamentally a question about achieving consensus between strangers without a judge or a god king or some other kind of person wielding abstract power derived from permissive authority. For at least 10,000 years, sapiens have done this the same way animals do it, using a physical power projection protocol we call warfare. The problem Nakamoto faced with determining how to establish zero-trust and egalitarian control authority over bit power is therefore not merely a challenge faced in distributed computing. This is a challenge that sapiens have encountered since at least the dawn of the Neolithic Age. Sapiens have been struggling to figure out a zero-trust and permissionless way to manage valuable resources and establish pecking order without injuring each other, and they have never succeeded to date. The most they have been able to achieve is creating temporary and fleeting reprieves from the destruction and injury of warfare. They have never been able to remove the destruction and injury of warfare altogether. If Nakamoto successfully solved the challenge to which he's often given credit, that could not just mean he solved a core challenge in computer science. That could mean he solved a core challenge for agrarian civilization. He created a non-lethal form of warfighting. In other words, he created Softwar. It is difficult to understate how big a deal it would be if it were true that Nakamoto did indeed discover a way for global society to achieve zero-trust, egalitarian, and permissionless control over bits of information passed across the internet. That would mean Nakamoto figured out a way for global society to establish zero-trust, egalitarian, and permissionless control authority over many of digital age society's most precious resources, without requiring kinetic, thus fratricidal, warfare. From this perspective, the fact that people have arbitrarily decided to call the bits of information secured by the Bitcoin network a coin seems trivial in comparison to the fact that Nakamoto may have discovered how to build a Softwar protocol that society could use to decentralize the internet and physically countervail the abstract powers and control authorities of those who are systemically exploiting its current architecture, which would include, but is not exclusive to, nation-states. The core concepts of power projection theory bear repeating. Humans already know how to establish zero-trust, egalitarian, permissionless, and decentralized control authority over resources. We have already developed a protocol where different populations of people who can't trust each other settle disputes and achieve consensus on the legitimate state of ownership and chain of custody of resources without the use of trusted third parties wielding some form of abstract power. In other words, rank, admin rights, or server owner, and control authority in some form of abstract power hierarchy. Society already knows how to leverage physical power in an inclusive, unbounded, and systemically exogenous way to achieve decentralized control authority over resources. The protocol is called warfighting. Therefore, what makes Bitcoin special isn't just that it allows for a bunch of people across the world to establish zero-trust, egalitarian, permissionless, and decentralized control over precious resources, because we already do that with warfare quite effectively. Hence why Earth's natural resources are split across 195 different countries. What makes Bitcoin special is how it achieves this same end state. It does it electronically through cyberspace, rather than kinetically through sea, land, air, or space. If it is true that Nakamoto solved the problem he is given credit for solving, then that could imply he also solved a much bigger, much larger scope problem that has been plaguing society for thousands of years. The problem of how to establish control authority over precious resources, how to settle disputes, how to establish dominance hierarchies, and how to achieve global consensus on the legitimate state of ownership and chain of custody of property, but do it all in a way that requires no god kings, no bloodshed, and thus circumnavigates the threat of fratricide or mutually assured destruction. Section 5.11.8 Bitcoin is zero-trust, permissionless, and decentralized control over a precious resource, itself. This section summarizes all the concepts discussed so far. Bitcoin appears to be a globally adopted physical power projection protocol, or Softwar protocol. The first war that agrarian society appears to be fighting using the Softwar protocol is a war to determine who has control authority over bit power, as well as a war to establish consensus on bit power's legitimate state of ownership and chain of custody. Just like other resources that agrarian society routinely fights over, for example, land, the complex emergent effect of this soft war is decentralization of control over bit power, where people are free to compete for access in a zero-trust, permissionless, and egalitarian way. But unlike other battles, this one is completely non-lethal. The term bit power is not a metaphor like other software specifications. Bit power is, quite literally, bits of information created by state changes of physical power, created by society through their global electric power grid. By doing this, the Bitcoin protocol utilizes society's power infrastructure as a planetary-scale computer that isn't under the consolidated control of a single person or organization. The bits of information created by this planetary-scale computer are unique in comparison to other bits of information on the internet, because they're reverse optimized. In a world where bits are becoming exponentially less scarce and less physically costly to produce, bit power is designed to become exponentially more scarce and more physically costly to produce. This gives bit power unique emergent properties that are irreproducible by ordinary computers running ordinary computer programs. By developing APIs, application programming interfaces, which require computer programs to utilize bit power, it is possible to impose severe, physically prohibitive costs on people and their programs in, from, and through cyberspace. This capability has the potential to make bit power quite valuable for applications like cybersecurity, or situations where computer programmers want to produce real-world physical properties, like physical scarcity or decentralization, rather than producing virtual illusions of physical scarcity or decentralization. It is already incontrovertibly true that proof of work works for cybersecurity, because Bitcoin uses proof of work to keep its own proofs of work secure against systemic exploitation. This confuses some people because it's recursive. Bitcoin is proof of its own merit as a cybersecurity system. Using the Bitcoin Softwar protocol, people are projecting real-world quantities of physical power to earn the right to account for the legitimate state of ownership and chain of custody of each sequentially reusable bit of bit power. As a result of this electric power competition, aka Softwar, the protocol is proving itself to be capable of making it physically impossible for anyone to justify the physical cost of exploiting it, even the most powerful nations in the world. This is how Bitcoin demonstrates its own merit as a cybersecurity system, which can physically countervail cyber attacks, not strictly a monetary system. It is clearly working as a new type of power projection technology, which allows people, to include entire nations, to keep the bits of information encompassing the property and policy they value secure against attacks, by empowering them to impose severe, physically prohibitive costs on belligerent actors which may or may not include nations. As demonstrated by Admiral Columbus and his plot to convince native Jamaicans to forfeit their resources to his crew, who had been oppressive to their Jamaican hosts, there is nothing limiting a person or a crew of people from exploiting a population's belief system to give themselves centralized and unimpeachable control authority over the population's resource, except for one thing: the physical power competition they would have to win against people who refuse to allow their belief systems to be exploited. This highlights a complex emergent social benefit of warfighting that many overlook. War physically prevents people from creating, encoding, consolidating, and centralizing abstract power and control authority over resources by exploiting a belief system. This is especially important to note in the 21st century because software fundamentally represents a belief system that is highly vulnerable to exploitation. The author explained in the previous chapter that warfighting is valuable to society because it gives people the opportunity to engage in global-scale physical power competitions to physically constrain and decentralize the reach of people with too much abstract power and control authority over resources. We know this is true because we know that warfare is the reason why control over Earth's natural resources is currently decentralized across 195 different nations. Bitcoin takes this exact same type of global power competition, but converts it into an electric form rather than a kinetic form. Bitcoin, therefore, clearly functions as an electro-cyber warfighting protocol. People are using Bitcoin to create and compete for zero trust and permissionless access to a scarce and irreproducible supply of reverse-optimized bits of information that can be transferred, received, and stored via cyberspace, but remain under no organization's centralized or unimpeachable control. Why would digital age society want a Softwar protocol? To preserve their freedom of action in the international thoroughfare we call cyberspace. To preserve their access to the bits of information they value. To protect and defend their ability to pass bits of information across cyberspace in a way that can't be interfered with or systemically exploited by people wielding and abusing their abstract power over computers. The physically secured bits of information that are being passed across proof-of-work computing networks like Bitcoin could potentially represent a vital new resource that 21st century society could need to combat cyber tyranny and keep themselves physically secure while operating in cyberspace. To that end, proof-of-work protocols like Bitcoin could give people the freedom to fight for zero trust and permissionless access to their most valuable bits of information the same way they have always fought for zero trust and permissionless access to their most valuable resources. Proof-of-work protocols offer the same might is right pecking order heuristic that has been battle-tested by 4 billion years of natural selection. And those who learn how to project physical power in the most clever and resourceful ways win the right to write the ledger to account for those bits. The physical power competition for access to and control over Bitcoin's bit power not only keeps the system decentralized and secure, it also makes the issuance and consensus mechanism unbiased. Like physical power itself, the Bitcoin protocol makes no ethical, moral, theological, or ideological judgments about those who use it. This makes Bitcoin perfectly fair and perfectly aligned to nature's proven method for settling disputes, managing resources, and establishing pecking order. This is the same method agrarian society already uses to establish their dominance hierarchy over Earth's limited resources, despite how much they like to use their imaginations and roleplay like they don't. In summary, using power projection theory, the author asserts it's not that Bitcoin solves the Byzantine general's problem, which makes the protocol so special. It's how it solves this problem. What makes Bitcoin remarkable is that it appears to have created a non-lethal equivalent to warfighting that achieves the same complex emergent benefits of traditional warfare, using the exact same social protocol of engaging in a physical power competition to establish pecking order over a vital resource, in a zero-trust, permissionless, and egalitarian way. But it removes the mass in these power competitions and swaps it with energy, thus eliminating the capacity for human injury and intraspecies fratricide. In other words, Bitcoin performs the same function for a pack of humans as antlers do for a pack of deer. This implies that Nakamoto didn't just create a peer-to-peer electronic cash system, he created human antlers. Section 5.12 Mutually Assured Preservation. The US dollar enjoyed great trust around the world, but for some reason it began being used as a political weapon, imposing restrictions on use. They began to bite the hand that feeds them. They'll collapse soon. Many countries in the world are turning away from using the dollar as a reserve currency. They restrict Iran in its dollar settlements. They impose some restriction on Russia and other countries. This undermines confidence in the dollar. Isn't it obvious? They are destroying it with their own hands. Vladimir Putin. Section 5.12.1 Securing Trade Routes and Preserving Freedom of Action in a New Thoroughfare, Cyberspace. One of the core functions of a military is not to secure a nation's borders, but to secure a nation's trade routes. The U.S. Navy, for example, exists to secure trade routes and preserve freedom of action in, from, and through the maritime domain. In whatever domain a nation relies upon to exchange goods, they tend to need a military to physically secure their ability to exchange goods and preserve freedom of action in that domain. Else, they become vulnerable to denial of service attacks. Imagine if the entire ocean was under the complete control of a single organization, and every nation who wanted to exchange goods across the ocean tacitly needed the permission of a single organization to do it. Would it be reasonable to believe a single organization in control of the entire ocean can be trusted not to exploit their control? Would it be reasonable to expect other nations to be pleased with a situation where they must have the tacit permission of one organization to access the ocean, establish trade routes, and exchange goods? The answer to these questions is probably not. Yet, this trust-based, permission-based system is exactly how cyberspace currently functions. We have established that computers are state machines. A network of computers connected together creates a state space which transfers, receives, and stores bits of information. Some call this state space an intranet or internet. Others call it cyberspace. Because these are abstract names, it would be just as accurate to call cyberspace an ocean. This ocean, created by a network of computers, functions as a new domain through which nations exchange a vitally important new type of good, bits of information. Over the span of a single human lifetime, this cyberspace ocean has become a very important domain upon which nations rely for the exchange of vital bits of information. Many different bits of information have value, but among the most valuable bits of information that nations like to exchange are bits of financial information, which facilitate international trade and settlement. Right now, the ocean through which nations exchange most of their bits of financial information is under the complete control of a single organization. This extraordinarily asymmetric amount of abstract power and control authority is derived from the fact that one nation controls the network of computers facilitating the exchange of these bits of information. The organization which has administrative control over this network has abstract power over the vital bits of information transferred, received, and stored on it. This abstract power gives them complete, unimpeachable, and centralized control over this entire ocean that many of the world's nations rely upon for the exchange of some of their most vital goods. If any nation wants to use this ocean to set up trade routes and exchange their highly valuable financial bits of information on it, they tacitly rely on the permission of a single organization to do it, and they must implicitly trust that organization not to exploit their control over the domain to inhibit their freedom of action. This system of information exchange between nations is currently a trust-based, permission-based, and inegalitarian system that is clearly vulnerable to exploitation. The United States has conclusively demonstrated this by denial of service attacking Russia from telecommunications networks such as the one controlled by the Society for Worldwide Interbank Financial Telecommunications, SWIFT. This begs a question. Why would any self-respecting nation who wants to have sovereign access to information exchange across the cyber domain subscribe to a permission-based system like this, when those permissions can be revoked at any time? One explanation could be that they simply don't have a viable alternative. It's hard to think of any computer network used in telecommunications which isn't under the unimpeachable control of some group of people. There might not be a viable way for nations to exchange bits of information using a telecommunications network without relying on a computer network that's still under some group's permissive controls. In this scenario, if a nation were to be denial of service attacked by SWIFT, for example, they would have no choice but to adopt some other computer network to exchange their bits of financial information. The challenge, of course, is that the other network would be equally as systemically insecure as SWIFT, because it would still be under the permissive control of some other group of people. With the current architecture of the Internet, there doesn't seem to be a way that nations can use computer networks and not be vulnerable to this form of exploitation. This would change if a planetary-scale computer were connected to the Internet, over which no organization could gain and maintain complete or unimpeachable control. If society were to adopt a protocol like Bitcoin that leverages the globally distributed electric power grid as a planetary-scale state mechanism, over which no single person, organization, or nation can physically afford to have centralized and unimpeachable control, then the state space of that state mechanism would represent a special new thoroughfare which nations could utilize to exchange their most valuable bits of information in a zero-trust, permissionless, and egalitarian way. Nations could theoretically use this planetary-scale computer to set up their digital trade routes, passing all bits of information they want to keep secure against denial-of-service attacks and other systemic exploits. It would be in a nation's best interest to set up something like this, considering how it's always been the responsibility of government to keep trade routes open and preserve freedom of action in every domain they operate. There's simply no reason to expect the cyber domain to be an exception to other domains in this regard. Herein lies one of the most critical insights of Bitcoin that might be overlooked. If the technical theories presented in this thesis are valid, and it's true that proof-of-work protocols like Bitcoin utilize the global power grid as a planetary-scale computer, which adds a special new state space to the existing state space of the Internet, then that new state space could represent the first truly zero-trust, permissionless, and egalitarian digital trade route in cyberspace that nations may come to rely upon to exchange their most valuable bits of information. An obvious first use case for this technology is to preserve the freedom of exchange of financial bits of information needed for international trade and settlement. But there would likely be several additional use cases. How might nations physically secure their ability to exchange their most valuable bits of information and preserve their freedom of action in this new, strategically advantageous trade route within the cyber domain? The same way they already do for land, sea, air, and space, by utilizing their specialized group of physical power projectors called the military to impose severe physical costs on those who impeded their freedom of action. With this concept in mind, the reader is invited to consider how some nations have already begun to adopt the Bitcoin network to exchange valuable bits of financial information needed for international trade and settlement. El Salvador is even raising bonds to subsidize the development of their own portion of the Bitcoin network, which converts their country's geothermal power into bit power. By doing this, El Salvador is actively working to secure zero-trust, egalitarian, and permissionless access to this special part of the Internet, under no organization's centralized and unimpeachable control. And they're actively demonstrating to other nations that it's working at keeping their valuable bits of information secure. Based on the precedent set by El Salvador, one could argue that nations are beginning to see how strategically vital it is for them to physically secure their access to this special piece of the Internet, where other nations can't prohibit them from exchanging their bits of information. To secure access to this unrestricted place in cyberspace against foreign interference, nations appear to be learning that they must create services dedicated to the projection of real-world physical power in, from, and through cyberspace, just like they already do for land, sea, air, and space. Nations appear to be learning how vulnerable they are to denial of service attacks by the system administrators of the computer telecommunications networks they choose to use. The actions taken by organizations like SWIFT against Iran and Russia have showcased to the world that whoever controls the network of computers managing the valuable bits of information they rely upon tacitly has complete and unimpeachable control over them. Nations are beginning to see that a zero-trust, permissionless computing network that enables bits of information to be transmitted, received, and stored without the threat of denial of service attacks or other forms of systemic exploitation are a vital national strategic security priority. Not just for financial bits of information, but for any kind of information. This would imply that Bitcoin has become widely recognized as a national strategic security imperative. El Salvador's actions demonstrate that nations are already beginning to recognize Bitcoin as a candidate solution. If Bitcoin were to be adopted by other nations, that could validate it as a systemically secure and strategically important computer network. To date, no nation has been able to surmount the enormous physical cost required to denial-of-service attack or systemically exploit Bitcoin's bits, including and especially nuclear superpowers. That's noteworthy, and nations appear to be taking notice. Section 5.12.2 Why build an electro-cyber militia when you can just subscribe to one? If the author's theory on Softwar are valid, then national adoption of Bitcoin could be envisioned as the adoption of an electro-cyber militia to protect and defend a nation's valuable bits of information. Nations like El Salvador are creating their own hash force, a service dedicated to projecting physical power to preserve their country's freedom of action in, from, and through cyberspace by imposing severe physical costs, aka watts, on anything that seeks to deny their sovereign right to freely exchange bits of information. But even if El Salvador didn't elect to build their own hash force, by simply choosing to use the Bitcoin network as the domain through which they exchange their financial bits of information, El Salvador would still be inheriting the security capabilities of the Bitcoin network, as if subscribing to a military-grade physical security as a service protocol. From a systemic perspective, Bitcoin functions similarly to how a militia functions. A large group of people project lots of physical power to preserve freedom of action within a particular domain, giving nations the ability to exchange goods, in this case, bits, with other nations without interference. The form of the militia is different because the form of the domain is different. Cyberspace is disembodied and transnational, so it makes sense that a cyber militia would also be disembodied and transnational. Something remarkable about the disembodied and transnational form of Bitcoin's security infrastructure is that it appears to be highly resistant to kinetic strikes, including strategic nuclear strikes. Bitcoin's infrastructure is spread across the world and is comprised of the globally distributed internet, power grid, and all the people running these systems. Because it's a decentralized network, the only way to destroy it is to destroy the whole network. This would suggest that the only way to destroy the Bitcoin infrastructure is to destroy both the internet and the global electric power grid. While this is theoretically feasible, it is not practically feasible because of the kinetic power projection paradox discussed in section 4.12. Our species would likely go extinct sooner than we would be able to destroy all the physical infrastructure of the internet and the global electric power grid. We may technically have the capacity to destroy Bitcoin's infrastructure, but because of the kinetic power projection paradox, it appears to be too expensive to do so. In other words, the BCRA of destroying Bitcoin is simply too low to justify. Therefore, not only do nations gain the physical benefits of a global-scale electro-cyber militia when they adopt the Bitcoin network as the means through which they exchange bits of information on the internet, they also appear to gain free access to a non-lethal security system that is, at least practically speaking, impervious to nuclear strike. In other words, nations which adopt Bitcoin gain access to a global-scale physical defense infrastructure that can empower them to stand up to nuclear-armed superpowers. Section 5.12.3 Raising hash forces to preserve zero trust and permissionless access to the Bitcoin network. With new physical power projection capabilities come new national strategic security strategies. In Bitcoin's case, nations now, at least theoretically, have a way to ensure that certain organizations in charge of certain telecommunications networks, for example, SWIFT, cannot abuse their abstract power and control authority over the network to denial of service attack nations who have a sovereign right to freely exchange bits of information across the internet. And because Bitcoin's physical power projection technology is electric rather than kinetic, this new strategy doesn't appear to be limited by the kinetic power projection paradox. This could mean that Bitcoin represents a key enabling technology for a new national strategic security strategy that could overcome a nuclear stalemate. For the sake of argument, let's assume the theoretics presented in this chapter are valid, and that the bits of information exchanged via the Bitcoin network do indeed represent reverse-optimized bits of information that are physically costly to transmit, receive, and store, giving them unique properties that are useful for many applications. Let's assume that securing zero trust, egalitarian, and permissionless access to these special bits becomes increasingly recognized as a national strategic opportunity. Any nation that follows in El Salvador's footsteps in adopting the Bitcoin network as the domain through which they exchange bits of information would also inherit the same baked-in physical security benefits of Bitcoin's global-scale nuclear-resistant defenses. These nations would effectively be subscribing to the security services of Bitcoin's globally decentralized electro-cyber militia, the same way a nation does when it subscribes to another nation's military for defense. It's a cost-effective strategy, but it's also a trust-based and permission-based strategy. By subscribing to Bitcoin's cyber militia as is, without contributing their own physical power and hashing infrastructure, a nation would tacitly be trusting in that militia not to denial of service attack them. The possibility exists that everyone participating in the network could unite against a given nation and withhold their valid transaction requests. Fortunately, the easy way to prevent this threat is for the nation to have its own hash force. This would allow them to utilize their own physical power projection capacity to guarantee they maintain ledger writing permissions. In effect, a nation would be building their own electro-cyber militia and attaching it to Bitcoin's combined electro-cyber militia to preserve permissionless access to the network. If this scenario were to play out, it would represent a global-scale international soft war for access to the Bitcoin network and its underlying bits of information. But unlike other global-scale international wars, a Bitcoin soft war would have far different strategic dynamics that would lead it to a much different end state. The author calls this special end state mutually assured preservation. Section 5.12.4 Solving the Kinetic Power Projection Paradox. As discussed at the end of the previous chapter, sapiens have a knack for building highly efficient power projection technologies, which empower populations to win physical power projection competitions called wars. After more than 10,000 years of practice perfecting the craft of physical power projection, sapiens appear to have reached a stalemate due to what the author calls the kinetic power projection paradox, a situation where society has become so efficient at a particular method of kinetic power projection that it is paradoxically too inefficient to use because of how much mutual destruction it would cause. To date, strategic nuclear warheads appear to be the most efficient kinetic power projection capacity ever invented by sapiens in terms of size, weight, and effort. Unfortunately, this technology is so efficient at projecting massive quantities of physical power that it does not appear to be practically useful. A full-scale war between two nuclear-armed nations would most likely be a war without winners. It's hard to solve a dispute if both sides are mutually destroyed. Ironically, the most efficient kinetic power projection technology ever created, nuclear warheads, appears to have created the most inefficient way to settle international policy disputes. Nations tacitly validate the existence of a nuclear stalemate caused by the kinetic power projection paradox when they pursue far less efficient kinetic power projection strategies to settle their disputes, manage control authority over resources, and determine consensus on the legitimate state of ownership and chain of custody of their property. Instead of using highly efficient power projection technologies like tactical nuclear bombs, they use non-nuclear weaponry like kinetic munitions to settle their disputes. Since the discovery of nuclear power, this strategy of deliberately using less efficient non-nuclear power projection technologies has only succeeded at settling minor disputes between asymmetric powers. It's still not clear whether it's actually possible for two nuclear-armed nations to settle major disputes using non-nuclear power projection technology. This would require one nation to be willing to surrender to another despite having the capacity to mutually assure the destruction of the nation to which they're surrendering, and that doesn't seem like a realistic scenario. It seems far more likely that a nation would sooner accept a stalemate than surrender to a nation they could destroy, and nuclear warheads are what give nations the former option rather than the latter. However, if we assume that it's still possible for two nuclear-armed nations to settle a major dispute without using nuclear technology, this doesn't resolve the kinetic power projection paradox, or bypass the risk of mutually assured kinetic destruction. As discussed in the previous chapter, forking the evolutionary path of kinetic power projection technology development into a non-nuclear direction still leads to the same dead end. By attempting a fork, modern society would likely continue to do what they have done so demonstrably well in the past, and develop incrementally more efficient kinetic power projection capabilities, until they discover yet another way to mutually destroy each other, except this time without nuclear warheads. Therefore, the strategy of using deliberately less efficient non-nuclear kinetic power projection technologies seems likely to cross the same threshold as nuclear technology did, where it becomes too efficient to be practically useful, aka crossing the kinetic ceiling. A speculative example of a kinetic power projection technology that could follow nukes in crossing the kinetic ceiling is massive-scale swarms of millions of highly maneuverable, artificially intelligent killer drones. It seems unlikely that two nations would be able to utilize kinetic physical power competitions to solve major disputes or secure access to resources in a zero-trust, permissionless, and egalitarian way if both sides of the conflict had access to strategic nuclear missiles as well as command over swarms of millions of highly intelligent killer drones. This situation seems like it would easily lead to another stalemate at both the strategic and tactical levels, using both nuclear and non-nuclear technology. Interestingly, Bitcoin appears to solve this paradox. Global-scale physical power projection competitions, enabled by Softwar protocols like Bitcoin, appear to be able to solve this type of quagmire by bypassing the kinetic power projection paradox altogether. By using a non-destructive form of electric power rather than a highly destructive form of kinetic power, hash forces would theoretically be able to compete for permissionless access to valuable resources exchanged across the Bitcoin network, without the threat of mutually assured destruction. Nations would theoretically be able to increase their electro-cyber power projection capacity and efficiency ad infinitum, without it becoming too destructive to be practically useful. No matter how competitive an electro-cyber power competition, in other words, a hash war, gets, it seems unlikely that it could lead to a state of mutually assured destruction, because there's nothing inherently destructive about developing increasingly efficient forms of electric power projection technology. In fact, society could potentially benefit from this power competition. It would motivate society to search for increasingly more clever technologies to generate more power more efficiently, as well as develop faster and more efficient hashing computers. Whereas the byproduct of a kinetic war is destruction of infrastructure and more expensive energy, the byproduct of Softwar appears to be the creation of more infrastructure and cheaper energy. This makes intuitive sense, using the theoretics presented earlier in this chapter. By turning the globally distributed electric power grid into a planetary-scale computer, society would theoretically be able to unlock Moore's law for the global electric power grid. Society would continually compete for incremental advantages by increasing the power projection efficiency and capacity of their portion of the global electric power grid. In other words, the portion of the planetary computer circuitry under their direct control. As a result, society could see exponential growth in both the efficiency and capacity of their power grids, just like they already do for their ordinary computers. Bitcoin falls directly in line with the evolutionary path of human power projection technologies developed across the past 10,000 years of agrarian warfare. This concept is illustrated in Figure 94, Evolution of Physical Power Projection Technologies, with Bitcoin shown as an end state. But more notably than that, Bitcoin represents the only globally adopted physical power projection technology that is practically useful for nations to settle major policy disputes, including but not limited to international financial policy disputes, establish zero-trust control over valuable resources, including but not limited to financial information, achieve global consensus on the legitimate state of ownership and chain of custody of property, including but not limited to digital property, and preserve freedom of action and exchange of goods across cyberspace, and do it all beyond the limit of the kinetic ceiling, where the kinetic power projection competitions are no longer practically useful. Combining these observations with the fact that running a hash force can be a profitable endeavor due to the high monetary value that people assign to the underlying bits of information exchanged across these networks, this means proof of power protocols like Bitcoin paradoxically have the potential to represent the most powerful and efficient physical power projection technologies ever discovered by agrarian society. Physical cost function protocols like Bitcoin make pragmatic sense. If it is true that society is already stalemated at a nuclear strategic level, then why go through the hassle of building a bunch of killer drone swarms to do battle with other killer drone swarms while humans watch from the sidelines? Are those drone fights going to achieve any meaningful advantage or resolve a nuclear stalemate? If society insists on trying to settle strategic policy or property disputes using human out-of-the-loop drone swarm battles, then what is the point of making it a kinetic battle? Why not put the drones on a rack, plug them together, and have them battle each other using electric power through cyberspace, rather than kinetic power through three-dimensional space? Technically speaking, Bitcoin is an international power competition using drone swarms. Instead of having machines compete against each other using kinetic power in the air, land, sea, or space domains, Bitcoin's machines are placed on a rack and they compete against each other using electric power in the cyber domain. It's the same game, but in a different domain, a domain that doesn't risk nuclear annihilation and doesn't appear to be stalemated. If the author's observations are valid, then it could mean that protocols like Bitcoin could effectively function as humanity's antlers. This technology could theoretically bypass the kinetic power projection paradox and give nations an opportunity to physically compete against each other in a zero-trust, egalitarian, and permissionless way that isn't stalemated and doesn't cause injury, which means it could generate very clear winners and very clear losers. By bypassing the kinetic power projection paradox, Bitcoin could represent humanity's ticket out of a potential bounded prosperity trap. Section 5.12.5 Escaping a fiery hellscape with a new method for zero-trust cooperation and physical security. During kinetic power projection competitions, in other words, traditional warfare, there is an existential imperative for agrarian society to sum their physical power projection capacity together, using cooperation techniques. Cooperation is first and foremost a physical power projection strategy, which allows a population to increase their mutual cost of attack to decrease their mutual BCRA, benefit to cost ratio of attack. Cooperation has enabled agrarian society to buy themselves increased prosperity margin and deter aggressors over thousands of years. These are the foundational primordial economic dynamics behind national strategic security. The massive-scale abstract power hierarchies, in other words, nation-states, we have today are the result of thousands of years of agrarian society learning how to cooperate at increasingly higher scales to keep themselves more physically secure against neighboring abstract power hierarchies. Today, agrarian society utilizes transnational power alliances, where multiple nations sum their physical power projection capacities together. However, like cyanobacteria and photosynthesis, sapiens and the abstract power hierarchies they build can backfire by causing society to become increasingly more vulnerable to systemic exploitation and abuse through their mutually adopted belief systems. Abstract power hierarchies inevitably break down for reasons discussed at length in the previous chapter. The general problem is that abstract power hierarchies are fundamentally trust-based cooperation techniques. Populations which utilize abstract power hierarchies must adopt trust-based belief systems, where people are given abstract power and trusted not to use it against their own populations. The larger and more asymmetric an abstract power hierarchy becomes, the more its believers become vulnerable to systemic exploitation and abuse. Trust-based belief systems are systemically insecure belief systems. Eventually, there is a point where the benefit to breaking people's trust is disproportionately higher than the cost of doing so. These inherent security flaws are important to note because today's nation-states are larger and more asymmetric than ever experienced by agrarian society. Today, it is not uncommon for 99.9999% of the population living within a nation-state to have to trust less than 0.00009% of the population not to abuse the abstract power and control authority appointed to them. This is a highly inegalitarian system that is vulnerable to systemic exploitation. Untrustworthy systemic predators would have much to gain if they wanted to exploit the high-ranking positions of these abstract power hierarchies, and there would be minimal physical cost for doing so, especially if the ruling class has nuclear launch codes. It is no secret that trust-based abstract power hierarchies have a well-documented tendency to break down and drive agrarian society back to war. War is highly energy inefficient and injurious, but it is the only zero-trust, egalitarian, and permissionless system where people are free to reset their dominance hierarchies by engaging in physical power competition. Therein lies the tragedy of agrarian society. The more society tries to avoid war, the more they must adopt systemically insecure, trust-based, inegalitarian, permission-based cooperation systems, like abstract power hierarchies, which tend to break down and lead directly back to war. Like cyanobacteria, agrarian society appears to be stuck in a bounded prosperity trap, which has driven it to the precipice of strategic nuclear annihilation. Now, populations are being cornered into adopting trust-based, abstract power hierarchies, with no ability to countervail their ruling classes if they become untrustworthy, exploitative, oppressive, or tyrannical. The emergence of new physical power projection technologies like Bitcoin fundamentally changes these power dynamics. Physical cost function protocols like Bitcoin give agrarian society the ability to sum their physical power projection together to increase their mutual cost of attack and decrease their mutual BCRA without having to trust each other. Instead of having to adopt systemically insecure, trust-based abstract power hierarchies to cooperate at larger scales and sum their physical power projection capacities together to impose increasingly more severe physical costs on aggressors, protocols like Bitcoin allow people to perform the same function in a zero-trust way. With physical cost function protocols like Bitcoin, anyone who contributes physical power to the system, as measured by hash rate, automatically increases the mutual cost of attack and decreases the mutual benefit to cost ratio attack for all users, including adversaries. The author hypothesizes this is because Bitcoin users technically utilize the same planetary scale state mechanism. By turning the global electric power grid into a planetary scale computer, two adversarial users living on opposite sides of the world stick together in a symbiotic relationship because they are technically using two sides of the same machine. Because they're both using the same planetary scale computer, if both sides were to attempt to marginalize the permissions of the other side by building larger and more powerful hash forces, they would increase the cost of attack and lower the BCRA of the same machine upon which they mutually rely. So long as no single hash force is allowed to gain and maintain majority hash rate, which is easy to prevent when all users have the freedom to add theoretically unlimited amounts of physical power or hash rate to the system from their side of the planet, then the addition of more physical power or hash to the system serves to increase the total physical cost required to gain and maintain systemically exploitable control over the system. In other words, as more physical power is added to the Bitcoin network by hash forces, the total physical cost required to achieve centralized control authority over the network increases, making it harder for any one entity to gain and maintain centralized control over the ledger. This creates an emergent behavior of the Bitcoin protocol, where the physical costs required to exploit the ledger can grow ad infinitum. No matter how much physical power is summoned by people in the competition for ledger writing administrative privileges over the Bitcoin network, the protocol can absorb all of it and channel it all towards increasing the total physical cost required to exploit the system. Nations could raise hash forces to secure their own permissionless access to the Bitcoin network. As they compete against each other for permissionless access to the ledger, all users directly benefit from the higher total hash rate and power consumed by the network, including and especially adversaries. Adversaries can become mutual beneficiaries because they're both contributing to different sides of the exact same planetary scale machine, which neither side can fully control. The protocol sums their physical power projection capacity together to create a single cost of attacking the network as a whole, causing nations to directly benefit from their adversaries' physical power projection efforts, even though they are directly competing against each other. The more people and organizations use their hash forces to compete against each other for permissionless access to the ledger, the more physical power and hash rate is required for any single hash force to gain and maintain centralized, thus exploitable, control over it. The more they compete against each other and add more hash, the more secure both parties become against denial of service attacks. It's a simple but remarkable emergent behavior of the system. Returning back to the core concept in power projection theory introduced in Chapter 3, cyanobacteria were able to escape the fiery hellscape of the Great Oxidation Event by evolving several new power projection tactics, to include learning how to stick together using multicellular cooperation. Both types of early multicellular cooperation represented zero-trust cooperation tactics. Cells didn't stick together because they trusted each other, they stuck together because they were literally stuck together, either through colonization or clustering. As a result of their zero-trust cooperative tactic, they were able to sum their combined physical power and escape their bounded prosperity trap together. Fast forward by about 2 billion years, and we arrive at modern human society, trapped in what could be described as another fiery hellscape. This time, it has taken the form of 10,000 years of agrarian warfighting, escalating all the way up to the threat of nuclear annihilation. With softwar technologies like Bitcoin, society could have discovered a technology which enables zero-trust cooperation at a global scale, which transcends national borders. By utilizing the same planetary-scale computer, two adversaries who have no capacity to trust each other can mutually benefit from each other's physical power projection efforts. They can use electric power to compete for zero-trust, permissionless, and egalitarian access to a vital new resource, bit power. And bit power itself allows them to impose theoretically unlimited physical costs on each other in a non-lethal way through a virtual domain. By fighting each other using the Softwar protocol, they paradoxically cooperate. Herein lies what the author believes to be the most compelling feature of the Bitcoin protocol. It could create an infinitely prosperous organism, as first discussed in section 3.7. By competing against each other for permissionless access to the Bitcoin network, adversaries serve each other by increasing the physical cost required to attack the network. Their competing power projection capacity is summed together to increase the overall cost of attack of the network. As a result of this ongoing power competition, network BCRA perpetually decreases. As users scale their hash rates ad infinitum, the network's cost of attack increases ad infinitum, and BCRA decreases ad infinitum, thus giving all users an infinitely expandable prosperity margin. So long as no single user can gain and maintain majority hash, everyone using this computer network benefits from the battle over control authority over it. As if by magic, the Bitcoin protocol turns adversarial physical power competition into a single, cohesive, infinitely prosperous organism, chasing after the same mutually beneficial end goal of improving security and preserving freedom of information exchange across cyberspace. Enemies become frenemies. Adversarial nations become de facto collaborators, working together on the same planetary scale computer, despite not trusting each other. Unlike the dynamics of kinetic power projection competitions shown in Figure 54, the end state of this global scale electro-cyber power projection competition is not mutually assured destruction, It's mutually assured preservation. This concept is illustrated in Figure 95. Comparison between hard and soft warfighting dynamics.